In this video, we will discuss the third factor of a hydrogen NMR signal, in this case, the multiplicity. So the multiplicity of a signal refers to the signal. How does the signal looks? We refer to that as the multiplicity. And we also refer to it as a splitting pattern as well. In proton NMR, every hydrogen will give us a signal. And that signal would have certain multiplicity to it. And the multiplicity of a particular signal from the hydrogen is then dependent on its number of neighboring hydrogen. Therefore, by analyzing the multiplicity of the signal, we know how many hydrogen that is surrounding a particular hydrogen that we are interested in. So the hydrogen in proton NMR are actually communicate with each other. And the reason why is because we can imagine as a hydrogen being a magnet. When we put two magnets close together, they will interact with each other. And we call that a communication, or the interaction with each other. And the extent of the communication is then the function of distance. And we can describe this by using J value. So J value are basically value that we would use to describe the extent of the communication between two hydrogen. For an example, in this molecule below, we have two hydrogen in this molecule. And because these two hydrogen right here are too far apart from each other, they do not communicate with each other. Imagine having two magnets, one magnet here and another magnet here. These two magnets right here are very far apart from each other, so therefore they do not communicate with each other. But on the other example, in this case, these two hydrogen right here are communicating with each other. So there is communication between these two hydrogen. And to describe the extent of this communication, we would have a J value for it. In this case, X here is the amount of the J value, and Hertz here is the unit of this communication. So what happens when there are communication between the hydrogen atom? Basically, the spin of one nucleus can alter the magnetic environment of another hydrogen, and therefore change its resonance frequency. So what that means is as follows. Every proton or hydrogen will give us a signal in proton NMR. And that signal starts out as a simple singlet. When there's communication due to the neighboring hydrogen, then the signal will get split. And the signal will then get split X number of times, dependent on however many neighboring hydrogen that it has. And the distance of the split is something that can be described by a J value. The stronger the communication between two hydrogen, because they're closer together, the larger the J value, and the clearer the signal would be. For an example, going back to this previous example, we see hydrogen A and hydrogen B, in this case right here, can communicate with each other. And here in this case, the J value to describe this extent of communication is 10 Hz, has been found experimentally. And so how did this affect these two signals right here? So here in this case, we will then see that hydrogen A will give us one distinct signal, and hydrogen B will then give us another distinct signal. Now, how does the hydrogen A and hydrogen B would look like? Let's now investigate that. So what will the signal look like? Let's now draw the signal for HA. Initially, HA, it will start out as a singlet, just like any other signal. Start out as a singlet. And because we see here in this case that HA is communicating with HB. And what will that do is that when there is communication, the signal will get split. It gets split into two, and now it becomes two lines. And how far apart these are together is dependent on the J value, here in this case 10 Hz. So therefore, this now become a doublet. So signal B would actually be a doublet. And similarly for HB. So initially, HB start out as a singlet as well. And here in this case, we see that HB has one communication with HA. There's one neighboring hydrogen that it has. So that will get split as well. Now, how far did this get split apart? It depended on the J value. And the J value of communication between HA and HB are 10. So in this case, 10 Hz as well. And therefore, this is now becoming a doublet. The chemical shift of HA is about 4.8 ppm and HB at 5.4 ppm. So if we were to now plot this NMR spectrum, is 0, 4, and 5 ppm. So at 5.4 ppm, we would see the HB signal. And the HB signal will split into a doublet. So at 5.4, we would then see the signal right here. And this would then be HB. As for HA at 4.8 ppm, so here in this case, 4.8 ppm, it would look like a doublet as well, which consists of two lines. And that's how it would look like. And here in this case right here, the ratio, the area under this curve of HB and HA are the same, a 1-to-1 ratio. And that will be the integration number. Let's now discuss the different types of communication among the hydrogens. Hydrogens that are too far apart from each other will not communicate with each other. And when they are close, then they'll be able to communicate. So how do we recognize the different types of communication? Let's now go over the different types of communication or the different coupling and their J value. So the first types of coupling is called the Vicinal Coupling. And this is a very, very common types of coupling that we would see in proton NMR. The Vicinal Coupling is also referred to as the 3-bond coupling because the two hydrogens are 3 bonds away from each other. Here in this case, these two hydrogens will be able to communicate with each other, and they are 1, 2, 3 bonds away from each other. And we would then also see that to be able to recognize these types of communication, we can count the bond, or we can also see that these are the hydrogen on 2 adjacent carbons. And the J value to describe the extent of communication between these two hydrogens are then dependent on the bond angle. These two hydrogens right here, the further the bond angle they are apart from each other, the higher the J value will be. For an example, so let's say here is the carbon on the front and the carbon on the back. These two hydrogens right here will be able to communicate with each other. And here in this case, the bond angle between these two hydrogens is 60 degrees. Therefore, its J value is anywhere between 2 to 5 Hz. If the two hydrogens are at a wider bond angle, for example, 120, then now the J value would be from 5 to 7 Hz. And when they're 180 degrees from each other, so you got these two hydrogens that are n-tied to each other. Now the J value will be 7 to 9 Hz. And if the bond angle among them is 0, in this case, these two hydrogens are eclipsing each other, the J value would then equal to 0 Hz. 0 Hz basically means no communication. So it's really important that we recognize what will be the bond angle between the two hydrogens in this vicinal coupling. In alkene, we can also observe these types of vicinal coupling as well. For an example, these two hydrogens in here are communicating through the vicinal coupling. It's also 3 bonds, 1 bond, 2 bond, and 3 bonds away from each other. And here in this case right here, the bond angle here is 180 degrees, and the J value for this type of coupling is 15 Hz. Now, if we were to have a cis-alkene instead, here in this case, these two hydrogens are communicating with each other. But in this case right here, their bond angle is 120 degrees from each other. So therefore, here in this case right here, the J value is only 10 Hz. And this is a very useful tool for us to be able to figure out what would be the what kind of alkene that the substance is by looking at this J value. If we were to have a trans alkene, that is when the bond angle would be 180 degrees and therefore have a larger J value. Versus if they're the cis alkene, they will have a much smaller J value to them. So that's how we can use to distinguish among cis and trans alkene. And for aromatic benzene ring, then we also observe a lot of this coupling as well. So here in this case, these two hydrogens are communicating through this vicinal coupling. And we also call this the ortho coupling as well, because these two hydrogens right here are ortho with respect to each other. And now we call this J ortho, and this in this case equal to 8 Hz. So overall, the vicinal coupling is a very common types of coupling. It depends on the bond angle. It can be anywhere between 0 to up to about 10 or 15 Hz. And how we would be able to easily recognize this is basically hydrogen that are on the carbon adjacent to each other. And the next types of coupling is the geminal coupling. Geminal coupling are basically referred to as a two-bond coupling. And these are the types of coupling that we would see for two hydrogens that are different and they are connected to the same carbon. If we were to have two hydrogens that are chemically different and they're connected to the same carbon, that's when we would observe these types of coupling right here. And this is called the geminal coupling. And the J value for this are normally negative value. But again, we don't care whether it is a positive value or a negative value, because a lot of time we'll be taking the absolute value of this J value. So for an example, in this molecule below, we would observe the geminal coupling between these two hydrogens. These two hydrogens are connected to the same carbon in here, and because due to R1 and R2, depending on what R1 and R2s are, if R1 and R2 are different, then these two hydrogens right here will have a different chemical environment and they will communicate with each other. Now, it's important to remember the following. The hydrogen would only communicate with each other if they are different. Similar hydrogens do not communicate with each other, but they would only communicate with different hydrogens. So here in this case, these two hydrogens are communicating through the geminal coupling. And the J value here is between 2 to 3 Hz. And on another example, these two hydrogens on this molecule right here are communicating through the geminal coupling as well. And the reason why is that these two hydrogens right here are not chemically similar. One hydrogen, this hydrogen, is much closer to this hydroxy group, whereas the hydrogen over here is further away from the hydroxy group. So they are not chemically similar, and therefore they will communicate with each other. And in this case right here, the J value is negative 12 Hz. So that's how we will be able to recognize the geminal coupling. And the third one is the allylic coupling. The allylic coupling is basically the types of coupling that we will see for allylic hydrogen. Now remember again the terminology. This hydrogen right here is called the allylic hydrogen. And the reason why is that it is connected to this allylic carbon. So here in this case right here, these two hydrogens will be able to communicate with each other. And we call this the allylic coupling. And this is basically a 4-bond coupling. And because they are up to 4 bonds, therefore, even though that their communication, they tend to be a weak communication that is not always present. and therefore the J value is anywhere between 0 to 3 Hz. When the J value equal to 0, that means no communication. So it can be anywhere between no communication to a small communication for this allylic coupling. An example of the allylic coupling is as follows. These two hydrogen, HA and HB, are communicating through this allylic coupling. So in this case, the J value is anywhere between 1 to 3 Hz. And another example is the communication between this hydrogen C and the HA. Again, they are communicating through this allylic coupling, and in this case 1.5 Hz. And the next types of coupling is called the homoallylic coupling. The homoallylic coupling is basically when we have two allylic hydrogen that are communicating with each other. So this is an allylic carbon, and this is another allylic carbon with hydrogen on them. And these two hydrogen will be able to communicate with each other. In this case, it is up to 5 bonds. Now recognize that there has to be a double bond in them in order for us to observe this homoallylic coupling. So both the allylic and the homoallylic coupling involve the communication through a double bond. So all of the bond between the hydrogen, there has to be a double bond in them. And also, this homoallylic coupling is a weak coupling and can be anywhere between 1 to 2 Hz and sometimes 0 as well. And the last types of coupling that we will discuss is called the long-range coupling. This is whenever we have signal, a hydrogen signal, that are 4+ bonds away from each other. And normally we would observe this in a ring system, functional group with a ring in them. And a lot of time they have a W conformation to them. An example is as follows. Here in this ring structure, these two hydrogen are communicating with each other. And they are 1, 2, 3, 4 bonds away from each other. Normally, they would not be communicating with each other, but because of this rigid ring structure, they end up communicating. And here in this case, we can see how this looks like a W. And we call this the long-range coupling. And in this case, it's 3 to 4 Hz. And moving on to a cyclohexane. These two hydrogen in here, these two equatorial hydrogen are actually communicating with each other. And in this case, they're also somewhere about 1 Hz. And again, we can see the W conformation in them. And that would be the best way how we would recognize them. And another example is this one. And in this case, its J value is 4 to 5 Hz. So that is the long-range coupling that is seen in ring structure. And now let's go over some of the common splitting pattern and their terminology so that way we can recognize them. So the signal in proton NMR are called different names. As for an example, singlet, doublet, triplet, doublet of doublet, quartet, multiplet, and so on. So let's go over each of these types of signal. First, what is a singlet? A singlet is basically the signal of a hydrogen without any neighboring hydrogen connected to it. So for an example, in this case right here, HA and HB in here do not communicate with each other. There's no types of coupling that we can recognize in here. And again, there's no long-range coupling because this is not a ring structure. And there's no homoallylic coupling either because there's no double bond in them. So we would then see that this does not belong to any of the types of communication that we have discussed. Therefore, the signal for HA is as follows. It starts as a singlet and it remains as a singlet. And similar for HB, it starts out as a singlet, and because it does not communicate with any other hydrogen, it remains a singlet as well. So both HA and HB would be singlets. And now a doublet. A doublet is basically the signal from a hydrogen that have one neighboring hydrogen that it communicate with. So here in this example below, both HA and HB will be split into a doublet. And the reason why as follows. Initially, both HA and HB start out as a singlet. When HA and HB are communicating with each other, it gets split once. And in this case, they get separated by this distance right here that is described by the J value. And in this case, we don't know what the J value would be, but it's important for us to remember the following. When HA is communicating with HB, it had one J value to it. And that J value would then be the same compared to the J value due to the communication between HB to HA. So it had same J value to them. And now the relative intensity of this signal right here will be 1-to-1 ratio. Because as we can have a signal that gets split into two, the two resultant signal now have similar intensity to them. So their relative intensity is 1-to-1. And now a triplet. A triplet is basically the signal from a hydrogen that have two equivalent neighboring hydrogen to it. And because of the two equivalent neighboring hydrogen, both of the J value are the same. For an example, here in this case right here, let's now do H. The HB, both HA and HB in this example right here will show up as a triplet. And the reason why is as follows. If we were to be looking at this HB, these two HB right here are similar. So therefore, they show up at one signal. And again, hydrogen that are similar will not communicate with each other, but they would only communicate with neighboring hydrogen that are different. So here in this case, HB will communicate with this HA and also communicate with this HA as well. When this HB communicate with this HA, its J value will be the same thing as the J value when this HB communicate with this HA, because these two HA right here are similar. So now let's draw the signal of HB. So let's say here HB again, everything starts out as a signal. When this HB first communicate with the first HA, it will get split into a doublet. And now the distance apart from them will then equal to x. HB then communicate with the other HA, and the resultant signal then further gets split up one more time. So here in this case, this signal further gets split. When it further gets split, one will go over here and half of it will go over here. And this signal over here gets split as one. So what we will then notice is that there is an overlapping signal in the middle. And here is the other signal. And the reason why that the signal in the middle overlap is because both the J value are the same. So therefore the resulting signal in here overlap. So thus the relative intensity for all of these three signals will be 1-to-2-to-1. So both HA and HB will show up as singlet. Now so the HA would also be a triplet as well. And again, these two HA right here are chemically similar, so they will show up at one signal, and they do not communicate with each other because they're chemically equivalent. And we will then see that this HA communicate with this HB, and let's say the distance now is x, that's the extent of this J value. This HA also communicate with the other HB, and because both of this HB are chemically equivalent, therefore the J value here is also x as well. So that's why over here they will be overlapping in the middle. And both HA and HB would be a triplet. And now let's go over a doublet of a doublet. A doublet of a doublet is whenever we have a doublet that now splitting into two other doublets. We will then call them a doublet of doublet. A doublet of doublet is observed whenever we have a hydrogen signal that have two non-equivalent neighboring hydrogen. So if a hydrogen have two neighboring hydrogen, and if those two neighboring hydrogen are not similar, that's when the hydrogen will show up as a doublet of doublet. And because the J value are different, Therefore, they do not overlap as to what we have seen in the case of a triplet. For an example, here in this case right here, HA, the signal of HA would be a doublet of doublet. And the reason why is as follows. Here in this case right here, we will then see that HA is communicating with this HB, and this HA right here would also be communicating with this HC. Now, this HB and this HC right here are actually not chemically equivalent. And the reason why is as follows. One of them is closer to the chlorine compared to the other. So this HB and this HC right here would not be chemically equivalent. And now, so let's say the communication between A to B, we call that with the XJ value, and between B and C, a YJ value, and from here to here, a G value. So let's see what happened. HA again would start out as a singlet. And when that communicates with the HB, it will split by this X distance in here. So that we can split into a doublet. And this resultant doublet right here further gets split because this HA also communicates with this HC. And let's say now this is the J value. So here in this case, the resultant signal gets split into J value. Because J is not equal to X, therefore the signal in the middle do not overlap. And therefore they show up as a signal with the same intensity as the signal on the left and the signal on the right. So therefore the relative intensity of this four signal will be 1 to 1 to 1 to 1. And therefore we would call this, or if we can redraw this, it will look something like this. So here in this case, this is called a doublet of doublet. And again, notice how the intensity of all of this signal are the same, 1 to 1 to 1 to 1 in terms of their ratio. So that when we will see a doublet of doublet. And a quartet. A quartet is a signal from a hydrogen. They have three equivalent neighboring hydrogen to it. And because all of the neighboring hydrogen are the same thing, therefore the J value are all similar. And that when the signal will get split into a quartet. For an example, here in this case right here, this HA right here will be split into a quartet. And the reason why is that it is communicating with this 3HB. The three hydrogen in this methyl group are actually equivalent due to the rotation of this carbon-carbon single bond. So therefore, when HA communicate with the first HB, it will be 1J value. Let's say this equal to X. When this HA communicate with HB, it will be another J value that is also the same thing, which is X as well. And from when HA communicate with the third hydrogen, the HB, it will be another X value. So let's now draw the signal of what HA would look like. HA initially start out as a singlet. And now when it communicates with the first HB, it gets split into a doublet. And now the relative intensity of this doublet will be 1 to 1. When HA communicates with the second HB, this resultant signal gets split one more time. So one over here and one over here. Same thing with the other signal. It would split one over here and one over here. And in this case, there is an overlapping in the middle because the two J value are the same thing. So the signal would only overlaps if the J value are the same. And when this HA communicate with the third hydrogen, the resultant signal will get split up one more time. So here in this case, one go in here, one go in here. And now when this signal gets split, two go over here and two come over here. And when this signal gets split, one go in here and one go in here. So in the end, we will then see that the relative intensity of these three signals will then be 1 to 3 to 3 to 1. That will be their relative ratio. And notice how this is different compared to a doublet of doublet. the doublet of doublet has relative intensity of 1 to 1 to 1 to 1. There are 4 signals, and that's their relative intensity. Versus in the case of a quartet, then it also split into 4 signals as well, but their relative intensity are 1 to 3 to 3 to 1. So if we were to draw this picture, this signal on the NMR spectrum, it will look as follows. So that would be the quartet. And lastly, a multiplet. A multiplet is basically the signal from the hydrogen that has many different neighboring hydrogen connected to it. And because now there's a lot of different coupling with a lot of different J value, the signal becomes fairly complicated and very difficult to analyze. So a lot of time, if we were to see signal between 5 to 6 signal, 5 to 6 signal and above, and it do not look like any pattern that we have seen, if it's not a quartet, not a doublet of doublet, or anything that we have recognized previously, we would simply refer to this as a multiplet. And that simply let us know that the signal that we are referring to has many different neighboring hydrogen connected to it. For an example, HC in this molecule will show up as a multiplet. And the reason why is as follows. First, it communicates with this HD, and that is through the Geminal Coupling. In this case, so there are 3 of this HD, and all of the J value are the same thing. This HC would also communicate with HB as well through the Geminal Coupling. And this HC right here would also communicate with this HA as well. So we can then see that when HC is communicating with the 3HD, it gets split into a quartet. And this quartet further gets split by this. So now we will have a doublet of a quartet. And this doublet of quartet further gets split one more time by this HA. So in the end, we will have a doublet of a quartet. And that's how we would refer to its name. A doublet of quartet. And it looked very complicated. So therefore, we would simply refer to this as a multiplet. And to make things simplified, we have adopted something that we call the N+1 rule to help us remember and be able to recognize the different types of signal. So basically, according to this N+1 rule right here, it is saying that the multiplicity of a signal is then equal to N+1 peak, where N is the number of equivalent neighboring hydrogen that the signal has. Again, N must be equivalent in order for us to apply this N+1 rule. If we do not have, if the hydrogen are not chemically equivalent, we cannot apply this N+1 rule. So here are some of the common splitting patterns based on this N+1 rule. So here N is the number of neighboring hydrogen. If a signal have no neighboring hydrogen, then it will show up as a singlet. And the intensity of the peak is 1. If a hydrogen have one equivalent neighboring hydrogen, it will be split into a doublet. And the relative intensity is now 1 to 1. If a hydrogen would have 2 equivalent neighboring hydrogen, it will now split into a triplet, following the N+1, where N is now equal to 2. So therefore we see 3 lines, and that is a triplet. And the relative intensity of this signal would then be 1 to 2 to 1. And similarly, if N equal to 3, 3 plus 1 equal to 4, it would then split into a quartet. And the relative intensity would be 1 to 3 to 3 to 1 among these different signals. And if there are 4 equivalent neighboring hydrogen, it would be a quintet. And if there are 5 equivalent neighboring hydrogen, then it would be a sextet. And the relative intensity will be 1 to 5 to 10 to 10 to 5 to 1. And if there are 6 neighboring hydrogen, it would then be a heptet. and their relative intensity will be 1 to 6 to 15 to 15 to 6 to 1. So that's how the signal would look like. And it follows something that looks like a Pascal triangle. Let's now apply what we have learned and try a few practice problems and use the n+1 rule whenever appropriate. So here in this case right here, let's determine the multiplicity of all the signals that we see in here. So first, let's now identify the unique types of signal that we can expect to see. On this molecule, we would expect to see one distinct signal for this 3 hydrogen, another distinct signal for this 2 hydrogen, and another one for this 2 hydrogen. So let's say A, B, C, and one signal for the hydrogen in here, and let's call that signal D. And these 2 signals in here are similar, and signal E. And again, these 2 metals right here are chemically equivalent. So therefore, they together give us one signal. The relative intensity of these 3 signals will then be as follows. Signal A will then be 3 times the intensity. Signal B will be 2 times the intensity. Signal C will be 2 times the intensity, since there are 2 hydrogen to make up that signal. Signal D will be 1 time the intensity, and signal E will then be 6 times the intensity. So that would be the intensity among all of these different signals. And now, what would signal A look like? Signal A would then be a triplet. And the reason why is signal A are communicating with the 2HB. And because 2HB are equivalent, therefore n+1 equal to 3. And that's why this is a triplet. And now signal B, what kind of multiplicity would it have? Here in this case right here, HB communicate with HA. When HB communicate with the 3HA, it becomes a quartet already. And this quartet further gets split 2 more times by the hydrogen from HC. So that quartet would then split into a doublet. So we will now have a doublet of a quartet. And that will further split up 1 more time. So we will then have a very complicated signal. So we simply refer to this as a multiplet. And now signal C will be split into a triplet, because signal C have 2 equivalent H hydrogen B. And signal C do not communicate with the signal D, and again because there's no double bond in them. And now signal D will then show up as a heptat. The reason why it is a heptat is because it has up to 6 equivalent neighboring hydrogen. 6 plus 1 equal to 7. So therefore it is a heptat. And now signal E. This signal E right here have 1 neighboring hydrogen to it. So therefore this will then split into a doublet. So we will then see this 2 signals together will become a doublet with an overall intensity equal to 6. So that's how we would draw the NMR spectrum of this molecule. Let's now combine everything together and draw what an NMR spectrum would look like. And we want to include the integration number, the chemical shift, and the multiplicity for all of the signal. So let's now try problem B, problem number 2 first. So why don't we take a minute and work on the NMR spectrum of this molecule before we go over the answer together. Okay, assuming you have done this already, let's now go over the answer together. So in this case right here, how many distinct signals would we expect to see? The answer, quite a few. There will be one signal, distinct signal for these 3 hydrogen. And now let's call this signal A. There is a hydrogen in here that is distinct, and that will give us another signal, and that will be the signal B. These 2 hydrogen in here will then give us another signal, and that will be the signal C. And signal C will then be 2 times the intensity. whereas signal B is 1 time the intensity, and signal A will then be 3 times the intensity. And this signal D right here with 2 times the intensity. And lastly, this methyl group, which is also another distinct signal. So let's call this signal E with 3 times the intensity. So overall, we will see 5 distinct signals for this molecule. And now, let's now go over the multiplicity and the chemical shape of this signal. First, what would signal A would look like? Signal A would then be a doublet, because it has only one neighboring hydrogen connected to it. So therefore, it will be a doublet with an overall intensity equal to 3. And now signal B would then be split into a quartet, because it has 3 equivalent neighboring hydrogen. And now signal C would then will show up as a triplet, because it have 2 equivalent neighboring hydrogen over here. And now signal D, because signal D are connected to the hydrogen from the signal B and the signal E, therefore it has a lot of neighboring hydrogen that are equivalent and not equivalent. So therefore we would expect a multiplicity to be quite complex. So here in this case, it will show up as a multiplet. So M for a multiplet. And lastly, the signal E. The signal E would show up as a triplet, because it have 2 equivalent neighboring hydrogen over here. And overall, the intensity of this triplet would then be 3 times. And now let's go over the chemical shape. What will be the chemical shape of this hydrogen right here? The chemical shape of this hydrogen right here is around 4.5 to 4.7 ppm. And the signal of this methyl group over here, this would then be, again, this is primary hydrogen CH, so therefore it will be about 1 ppm. And this 2 hydrogen in here, because it's right next to a carbonyl, which is about 2.1 to 2.2 ppm. And this hydrogen, this multiplet in here, because this is secondary, would be about 1.2 ppm. And lastly, this one right here, it is primary, so let's call this about 0.9 ppm. So those are the multiplicity and the chemical shape of all of this signal. And now let's sketch what its NMR spectrum would look like. So here's 0, and let's plot this all the way to 5 ppm in here. So 1, 2, 3 ppm. So first, the signal A will show up as about 1 ppm as a doublet. So if we were to now go to 1 ppm, we will see a doublet. And overall, its intensity is 3 times. So a doublet with the intensity equal to 3. So let's put that number on top, 3. So that shows that the ratio of this signal below is 3. So that would be our signal A. And now signal B would then be at about 4.5 to 4.7 ppm as a doublet. And overall, it have 1 time the intensity. So we would then go to 4.5 to 4.7 ppm. And in this case, a quartet with overall intensity equal to 1. A quartet look as follows. 4 different lines. And overall, this would then have 1 time the intensity. So the area under this signal is 1/3 compared to the area of this signal under this curve. And that would then be our signal B. And for our signal C, it is a triplet at 2.1 ppm. So we will go to 2.1 ppm, and now in this case, draw in a triplet. So that's how a triplet would look like, 3 lines. And notice that the line in the middle is more intense compared to the signal on the left and on the right. So here in this case, this would then be the overall intensity of this signal with respect to the other different signal will then be 2 times. And that would be our signal C. And our signal D would then be at 1.2 ppm, and it's 2 times the intensity, and it is a multiplet. So we would draw this signal as follows. So we would draw a lot of lines to show it is a multiplet. And here in this case, its intensity overall would then be 2, and that would be our signal D. And as for our signal E, it's now at 0.9 ppm. So now let's go to about 0.9 ppm in here and draw in our signal E. Our signal E would then be a triplet with an overall intensity equal to 3. So therefore, we would draw another triplet in here. And its intensity equal to 3 overall with respect to other signal, and that would then be our signal E. So overall, that would be the NMR spectrum of this molecule. Now, so let's discuss how did we estimate the chemical shift of this signal in here. Why did we estimate that it's somewhere between 4.75 to 4.7 ppm? One trick to determine or estimate the chemical shift of a signal whenever the signal has 2 things connected to it is as follows. Here in this case, we can see that this hydrogen in here is connected to a bromine and a carbonyl. Both of these are electron withdrawing group that can make this hydrogen in here very much de-shielded. So how did we estimate its chemical shift? Here is one rule of thumb right here. There's no guarantee that this would always work, but it will give us a very good approximate. So we will then see that when this hydrogen right here is next to a bromine, it will be somewhere about 3.7 ppm. And if a hydrogen is next to a carbonyl, is about 2.1 ppm. So we need to add them together. But we cannot add them together directly. This is how we would add them together. We would then take the bigger value plus 1/2 of the smaller value. So here in this case, 3.7 ppm plus 1/2 of 2.1 ppm, the smaller value, which equal to about 4.7 ppm. So that's how we would approximate the chemical shift whenever we have a hydrogen they connecting to different electron withdrawing group. We take the higher value and we add 1/2 of the smaller value, and that will give us a good approximate.